All right, so here is the video for the green trig review for your final exam. I'm using a different microphone for this one, so if they sound about the same, okay, whatever, but if you notice a drastic difference between the two or any issues with them, please let me know. This is actually my second time doing this because one of the issues with this microphone is that it eats batteries, and got on me 4 minutes in last time, and I didn't know it because it doesn't warn me. And then I just stood here and talked to myself the whole time. So I guess it was like a rehearsal. So now, the real deal. Matching. Right, so you can approach matching either way. You can read all these and then look for the answer over here, or you can read all these and see which one matches up. It's usually easier to muddle through the stuff with less on it than over here. So let's just read through what we have. We're looking for negative angle, reference angle, unit circle, degree, arc length, conversion factor for degrees to radians, quadrantal angle, radian measure, standard position angle, and coterminal angles. All right, so looking over here, a circle with radius 1. Well, that is a unit circle, and I had unit circle here, so this is A. 180, well, that's kind of vague. 180 could be the answer to a lot of things. But not any of these. It is degrees, but I really don't think that's it. Arc length, it's not a conversion factor. It is a quadrantal angle, so I don't know that that's really the best fit for this term, but it is an example of one, so we'll put a B with a question mark. If there's nothing else better, then that's probably our answer. Radian measure, standard position angle, coterminal angle. All right, so then we'll move on. So pi over 180. So I have pi over 180 and 180 over pi. Those are both conversion factors. One goes from degrees to radians, one goes from radians to degrees. Over here, you just have from degrees to radians. You don't have a radians to degrees over here. So if you want to change it from degrees to radians, you have to make sure you multiply a pi into it, which means pi is in the numerator. So this is C. Looks like I'm not going to use D anywhere, most likely. All right, angles with the same terminal ray. All right, so you can rotate multiple times, counterclockwise or clockwise, and you can end up in the same spot. And when that happens, they are coterminal with terminal, right? So same terminal side, or same terminal ray side, whatever. This is E. Okay, counterclockwise. When you go counterclockwise, that is a positive angle. When you go clockwise, that is a negative angle. So this is a positive angle. There's negative and no positive here, so I don't think I'm using F. Formula S equals R theta. S represents arc length, so that is my arc length formula, and that is here, number 5, so this is G. And initial ray, well, it's not negative angle, reference angle, degree, arc length, quadrantal, radian, standard position. I mean, a standard position angle and a quadrantal angle both have an initial ray, but that doesn't really fit that. I don't think I'm using H. 1/60th of a degree. Remember, you can have degrees, minutes, seconds. So 1/60th of a degree is a minute. Minute is not one of my choices. Don't think I'm using I. J, angle with the vertex at the origin, an initial ray on the positive side of the x-axis. That is a standard position angle. So that is J. Angle with the terminal ray on an axis. All right, well, that would mean it's not actually in a quadrant. That is really the definition of a quadrantal angle, so much better answer for this than B. So I don't think B is my answer there. I think that it's going to be K. Clockwise angle, right? So remember, counterclockwise is positive, clockwise is negative. I have negative angle in number 1, so that is L. M, portion of circle's area cut by a central angle. So that's a sector. Don't have that as one of my remaining choices. Smallest positive acute angle to measure back to the x-axis, and that is your reference angle. Some of you really need to practice on those. Well, actually, all of you do. You need to know them very, very well. Even when we come back for Christmas, you have to know your reference angles. You have to know your values. Those are things that we're not just doing it like now and then it's not going to matter. It's still going to matter. 1/360th of a rotation, that would be a degree. This is O. And then angle measure based on arc length. So arc divided by radius, that is how you get a radian. So that is P. All right, moving on. It says find a coterminal angle for the following in the same form. So if I am going to do radians here, then that means if to find a coterminal angle, you are going to add or subtract multiples of 2 pi, because that gives us a full rotation in one direction or another. So it just asks for 1. I'm going to do 2, because most likely you didn't do like a huge multiple of 2 pi. You probably did pi either positive or negative. Most likely positive is probably the first thing you would do, but because there can be more than one answer, there's actually an infinite number of answers. I'm going to go ahead and do like one of each, one with adding and one with subtracting. So when I take this 7 pi over 12, and I want to add to it 2 pi, but I need to get a common denominator. So 2 pi in terms of twelfths is going to be 24 pi twelfths. Okay. So when I add those two together, that is going to give me 31 pi over 12. And then I'm going to do 7 pi over 12 minus 24 pi over 12. So when I get that, that is going to give me a negative 17 pi over 12. Right. So then, for 3 pi fifths, I'm going to take 3 pi fifths, and I'm going to add 2 pi, but in terms of fifths, that would be 10 pi fifths. So that's going to give me 13 pi over 5. Right. And then I'm going to do 3 pi over 5 minus 10 pi over 5. So it's going to give me negative 7 pi fifths. For degrees, I'm going to add or subtract multiples of 360. So that means I'm going to get 200 plus 360 and 200 minus 360. So 200 plus 360 is 560 degrees. 200 minus 360 is negative 160 degrees. And then the negative 140 plus 360 and negative 140 minus 360. So that will give me positive 220 degrees and a negative 500 degrees. So those are your coterminal angles. And then those are important because if you know what's happening at 7 pi twelfths or 3 pi fifths, then the same thing is happening at all of the coterminal angles. Then the reference angles are very important and helpful for you to figure out your trig values and where you are in the circle and whole 9 yards. So you can, I'm going to draw some stuff that you may not necessarily always want or need to draw, but I want to make sure you're following my thought process since you can't see what I'm trying to point to unless I write it. But when you look at this and you want the reference angle, remember it's always the smallest or the shortest way back to the x-axis, and it's always positive no matter which way you rotate. So if I think in terms of sixths, 6 pi over 6 is pi. So that would rotate me around to here, right? So because this is pi. So if this is a little bit more than 6 pi over 6, I have to go 1 more pi sixths to get there, right? So that means that 6 pi over 6 gets subtracted, and I've got just pi sixths left. So my answer is pi sixths. And you should be able to, hopefully think through that with having, if you got to jot some stuff down every now and then, that's fine. But you don't necessarily have to draw a picture every single time. You want to get to the point where you don't need to. All right, so then 3 pi fifths. All right, well, 5 pi fifths is pi. So 3 pi fifths is more than halfway, so that gets me to like right about here, something like that, right? Because that's 3/5 of the way to over here. That means the amount that I have left to go to get here, this is my reference angle, right? I have 2 pi fifths left to get here, so this is 2 pi fifths. The degrees, 310, you're going to end up in the 4th quadrant, and you've got 50 degrees to go to get to 360. Negative 130, So I would start here and rotate this way, negative 130 is over here. I would have 50 degrees more to go, right? And my answer is a positive 50. Notice both of these have a reference angle of 50 degrees, even though one's in the fourth quadrant, one's in the third quadrant, one of them's even negative. Reference angle is always, always positive. All right, signs for the given trig ratio in all four quadrants. So remember we have all students take calculus. That tells you where things are positive. All of them are positive here, sine, tangent, cosine. So then along with sine, you also have cosecant. Along with tangent, you also have cotangent. Along with cosine, you also have secant, because these are all their reciprocals. So for tangent, I want to know, give the signs. So everything's positive here. And then tangent is also positive here, which means these are negative. Cosine, everything's positive here. Cosine is also positive in the fourth quadrant, which means it's negative here. Cosecant is the reciprocal of sine. So as far as the signage goes, that's what I'm concerned with. Everything's positive here, sine's positive here, things are negative there. I'm gonna pause and check my audio. Okay, I think it's working okay. All right, backside. We are going to convert these to degrees. So to convert to degrees, you are going to multiply by 180 over pi. And before you just start multiplying, some of you need to learn that not have so much random work every day. And it's not about having a messy paper or anything, it's about you doing things the hard way. I can multiply 3 times 180 and then divide by 5, but you are really making that harder on yourself than is necessary. These pi's cancel out. So this is really just like one big fraction of multiplying the numerators, multiplying the denominators, so I can cancel anything in the numerator. This is obviously reduced all the way, but I can reduce the 5 and 180. So 5 goes into 5 once, goes into 180. Well, 5 goes into 18 3 times, right, with 3 left over, so that gives me 30. 5 goes into 36 times, so I get 36. My denominator is now just 1, so really I just have 3 times 36, which is 108. This one I'm going to multiply by 180 over pi again. So my pi's cancel out. Can't reduce that anymore, but I can reduce this way. 3 goes into 3 once, goes into 180 60 times. Denominator's 1. 5 times 60, 300. Right, then multiply this by 180 over pi. Pi's cancel out. All right, now 12 is divided into 180, but you know, long division, really, unless you're doing it for like polynomial long division or whatever, really isn't something that should be your go-to thing, I think, because that ends up being a lot of guessing and checking for y'all, or you don't know what to do with your remainder if there is one. I mean, it would work out nicely here, but again, you need kind of better coping skills for other things. Let's say you didn't, 12 goes into 18 once with 6 left over, and then you can divide 12 into 60. Well, let's say that was just too difficult for you, or you get yourself confused. You don't have to divide the whole thing. If you're not even sure what to divide by, they're both even. So I'm going to divide them both by 2. So this gives me 6, this gives me 90. All right. Well, they're both divisible by 3, right? So 3 goes into 6 twice, goes into 90 30 times. Right, so now they're both even. 2 goes into 2 once, goes into 30 15 times. So in the denominator, I now just have 1. And in the numerator, I have 5 times 15. So multiply that a few different ways. But anytime you have multiples of 15, like if you have multiples of 25, you think in terms of quarters, because y'all can count money. If you have 15s, think in terms of time. Okay, 4 15s makes an hour. So it's an extra 15 minutes. So it's not 115, think of it that way. Or also do it in pieces. 5 times 10 is 50. 5 times 5 is 25. So together that is 75 degrees. Just figure out whatever works best for you. And again, I'm not saying you always have to do everything in your head. Try and do it, because clearly I'm writing stuff down here, but just find a way to get through things quicker and easier for yourself. All right, so to convert to radians, I have to multiply by pi over 180. So anytime I have that, I always want to put something that's not a fraction into a fraction. My pi's don't cancel out, obviously. But I can divide both of these by 10, because I can knock out those zeros. So now I have 20 and 18. All right, well, I can divide them both by 2, so this gives me 10. This gives me 9. can't reduce it anymore, so it is 10 pi over 9. I'm going to multiply this by pi over 180. Put that over 1. Right. I can again divide both by 10. Right? They're both even again, so that's going to give me 15 and 9. I can divide both of those by 3, so that gives me 3 and 5. That's the best I can do, so it is 5 pi over 3. I'm not saying you have to break it down into little pieces if you know what it is, but that's really more for those of you that don't automatically see it. Plus, sometimes it's quicker than trying to figure out what the biggest number is. Just do it, and then you're safer. All right, so then I'm going to multiply this by pi over 180. Put that over 1. Okay, so I can't knock out zeros here, but, I mean, again, they're both divisible by 12. You could start there. If you know that, or if, but don't spend too much time trying to figure it out. Hey, they're even, start there until you get it down to something you can reason through a little bit better. I've got that divided by 2 gives me 72. All right, well, 72 and 90, they're both divisible by 9, right? So that would give me 8 here and 10 here. Okay, so now they're even. So this gives me 5 when I divide by 2. This gives me 4 when I divide by 2. Now I can't reduce anymore. My numerator is 4 pi. My denominator is 5. Think smarter, not harder. Or if you have different ways, I'm not saying you have to reason my way either. If you have different ways that are quick and work for you, as long as they actually work every time and it's not some sort of trick you got lucky with, then do what you need to do. All right, so we're going to define define each in terms of x, y, and r. So remember, in a unit circle, x and y are just your x cosine and sine values. But this is for any circle when r maybe isn't 1. So you've got x, y, and r. So cosine is the x value over the radius. That's how you get just x when the radius is 1. So this is x over r. Secant is the reciprocal of cosine, so it's r over x. And cotangent is the reciprocal of tangent. Tangent theta is opposite over adjacent, which is y over x. So cotangent is x over y. All right, so now I want to find each exact value over here. So again, I'm just drawing this so that I can point to it and talk about it. When we go to 270, okay, here at 270, this is 0, negative 1. Your cosine value is your x, so it's just 0. Secant is 3 pi over 2. All right, well, 3 pi over 2 is 270. It's in the same spot. Secant is the reciprocal of 0 is 1 over 0. You cannot divide by 0, so that is undefined. Then we have pi. Pi is here. This is negative 1, 0. Sine is your y value, so it's just 0. Cosecant of 330, so 330 is over here. I've got 30 more degrees to go to get to 360, so that's my reference angle. I know it's not to scale, but it doesn't matter. You need the idea more than anything. So you're really looking for the cosecant of 330, plus you have to think about the signs here. All right, cosecant is the reciprocal of sine. So in the fourth quadrant, sine is negative. So I'm going to use my reference angle and my little hand trick, but I also have to pay attention to the signs. So since cosecant and sine have the same sign, different use of the word sine, in the fourth quadrant, sine is negative, so cosecant is also. So my answer is negative. Then I can use my little hand trick, and sine of 30 degrees is 1/2, okay? But I want the cosecant, which is the reciprocal, so the reciprocal of 1/2 is 2. All right, so then the cosine of 150. Cosine of 150, so here I'm at 150, my reference angle is 30. Cosine in quadrant 2 is negative, so I know this is going to be negative. And then the cosine of 30 is square root of 3 over 2. Secant of 7 pi fourths, right? So this is another one. Here, I'm going to draw a separate one for this. There's too much on there. So 7 pi fourths is almost 8 pi fourths. 8 pi fourths is 2 pi. So 7 pi fourths has a reference angle of pi fourths, because that's how much more I need to get to. Ooh, dang it. Sorry, let me make sure I didn't accidentally turn my mic off. All right. I have pi fourths as my reference angle to get here. So I have to think, first of all, secant, that's the reciprocal of cosine. So in the fourth quadrant, cosine is positive, so secant is also positive. So as long as I find whatever the cosine of pi fourths is and then take the reciprocal, it's going to be positive, and that's my same sign, right? So cosine of pi fourths is square root of 2 over 2. That. So that means it's going to give me 2 over the square root of 2. So when I rationalize that, that's going to give me 2 square root of 2 over 2, which just means it's the square root of 2. All right, circle applications. So this is where things started to get way worse for y'all because of me, because of the terrible job I did teaching this at first, and hopefully I ironed everything out. But so given that it's not nearly as difficult as I made it out to be that first day when I made no sense. Given the formula for the arc length, S equals r theta, find the arc length when the radius is 15 inches and the central angle is 60. Okay, so bottom line here on anything like this, make sure if you're supposed to use the radius, you're really using the radius, because on one of those things that y'all turned in, some of you weren't using the right thing on one of them. I know you know better. So here r is 15. Like maybe write that out so that you don't mess up on something. And when you're finding the arc length, your theta has to be in radians. So 60 degrees is pi thirds radians. That's what I have to use here. Okay. And it says, given the formula, find the arc length when the radius is 15 inches and the central angle is 60 degrees. All right, so I just substituted in S equals R, which is 15, times theta, which is pi thirds. So I can reduce that. That just gives me 5 pi. You got to have units because you got to make sure you understand what the heck is going on. This is arc length, and that therefore it is in inches. Okay. And you remember, you're not going to have a calculator, so there won't be any decimals, everything in an exact answer. So make sure you can work all of these problems without a calculator because you will not get one on the test. All right, given the formula for area of a circular sector, find the area of the sector when the radius is 12 millimeters and the central angle is 210. Okay, so radius is 12. Central angle is 210. All right, so the easiest way to figure out what the radians are is think about the reference angle. Right? So the reference angle for 210, that's 180 plus a little bit. It's 180 plus 30. Okay, so 30 is pi sixths. To get to 180, you're at 6 pi sixths. To go to 210, which is one more 30 degrees, that would give you 7 pi sixths. Okay, it really should be something you just kind of know, but really get to that point, able to come up with it. All right, so then we just substitute this in. My area is equal to 1/2 times 12 squared times 7 pi over 6. All right, so I'm going to go ahead and do 12 squared is 144. Half of that is 72. So 72 times 7 pi over 6, and I'm going to put this over 1, and then I can reduce. Right? 6 does divide into 72. It may not be something that just pops in your head. You should know that it does, but again, you can just start with dividing them both by 2. That's 3, that's 36. And then 33 does go into 36. 3 goes into 3 once, goes into 36 12 times. My denominator is now 1, and then my numerator is just 12 times 7. And do it in pieces, right? 7 times 10 is 70. 7 times 2 is 14. Add those two together and you get 84 pi. And again, units, this would be millimeters squared because it's area. Okay. So given that a Ferris wheel has a diameter of 280, so radius of 140, and rotates once in 80 seconds, so that means I have 1 revolution for every 80 seconds. Its angular velocity is blank radians per minute. Okay, so my angular velocity formula, angular velocity is a theta over time situation. Theta could be in revolutions, it could be any time, just whatever the problem tells you to do. And you don't, it gave us the I wrote out the radius so I could make sure I used it right if I needed it. I don't even need it. okay, didn't hurt me to write it down, just got to make sure I don't try and here. So I have to take the information that I know. What I know is revolutions per second. Okay, so I know that my angular velocity is 1 revolution for every 80 seconds. Okay, but I don't want it in revolutions per second. I want it in radians per minute. So I have to start converting. I need my revolutions to cancel out, and I can convert directly from revolutions to radians because I know that I have 1 revolution for every 2 pi radians. So now I've got this radians part taken care of. So now I have to get the minutes taken care of. If this is in seconds, I need my seconds to cancel out, and I can convert from seconds to minutes. I know that for every 1 minute, there is 60 seconds. Okay, so then I have my minutes taken care of. So now I have it in radians per minute because all the other units are canceled out, and then I can just reduce before I actually multiply. Let's start with this 80 and the 2. So I can divide them, well actually, let's start with the 60 and the 80 because I can divide them both by 10 and knock out the zeros. Right? So then I've got the 2 and the 8. 2 goes into 2 once and goes into 8 4 times. Right? So here I'm just left with 1. Here I'm left with pi. That's not going to cancel out, so I want to make sure I don't miss it there. And then I have the 6 and the 4. Well, they're both even, so divide that by 2 and get 2. Divide that by 2 and get 3. So I don't think there's anything else I can reduce. This is just 1. This is pi radians, and here's my 3 that I'm going to use. You don't want to get lost in all your canceling. None of that matters. I have to use this 2 in the denominator, a 1 that doesn't really matter when I'm multiplying, and a 1, and I've got my minutes. So that means when I multiply all this out, I just get 3 pi halves radians per minute. All right, so given that the point -1, -4 lies on the terminal ray of theta, find the 6 trig ratios. Okay, so -1, -4, something like this, but this isn't really to scale, but that's okay. -1, -4, so I need to find the radius. So I know that -1 squared plus -4 squared equals r squared. That's 1 plus 16 equals r squared, which means r is the square root of 17. Okay, so I'm looking for sine theta, cosine theta, tangent theta. I'm also going to need cosecant theta, secant theta, and cotangent theta. All right. So sine we know is opposite over hypotenuse. It's also the y value over the radius, so y over r. So that would give me a -4 over the square root of 17, but I have a square root in the denominator. So when I rationalize, that's going to actually give me -4 square root of 17 over 17. Cosine theta is your x over r, or adjacent over hypotenuse, so that's going to give me -1 over the square root of 17. And when I rationalize, I get negative square root of 17 over 17. Then tangent is opposite over adjacent, or y over x, so that's -4 over -1, which is just a positive 4. And we know that tangent's positive in the third quadrant. We go to cosine, but if I take the reciprocal of this, then I have to rationalize again. But sine is r, so cosecant is r over y, and so that is just square root of 17 over -4. Same thing here with secant. Well, cosine is x over r, so this is r over x. So that's the square root of 17 over -1, so it's just negative square root of 17. Cotangent, I can easily take the reciprocal of this, or since tangent is y over x, this is x over y, which is going to give me a positive 1/4. Okay? So that wraps up your reviews. Please let me know if you have any questions, and I think that you can all do very well on this.